We're very happy here to have Majid Hassanizadeh speaking today at ProLab. And well, Majid is a professor emeritus in hydrogeology at Uthrecht University. I would add legendary professor with a PhD from in civil engineering from Princeton University. And his field is two-phase flowing porous media, reactive transport, solute and colloid transport, etc., etc. I mean, basically all of porous media.
Don't worry.
And he's also co-founder and present director of Interpor, this International Society for Porous Media. And he's been instrumental in building that organization. And boy, does he follow it up. So we are in very good hands. And for us locally, he is a member of the scientific advisory board for that. So he's a person we take very seriously, and yeah, we're going to meet in the fall.
Yes, I look forward to that.
Next okay.
Thank you.
Yeah, so please.
Alex, for the kind introduction. It's great to be online. It's great to see where you're sitting. I have nice memories from the time I visited Trondheim and sitting there having lunch together. I hope indeed I'll be back sometime soon. So let me share the screen. Yeah, I guess you see my screen.
Yes. Yes.
Okay. Thank you for the invitation. Great pleasure to give this online lecture at your lecture series. Let's see where. I guess the title is not, yeah, because there was something from Zoom covering the title, but it's not, it's okay now. So I will talk about two-phase flow in industrial or manufactured porous media. I would like to acknowledge various collaborators who have been doing different parts of this research I present here. Is an overview research. Now, one of the things about this presentation is that I think it would be interested particularly to some petroleum engineers, this kind of presentation, because nowadays universities around the world, some of them are closing down petroleum engineering departments or renaming it or merging it with other departments. And there are students who are worried and wondering what will happen to them if they study petroleum engineering in 20 years within a fossil-free, fuel fossil-free world. And then the thing is that with your knowledge of flow and transport in oil reservoirs and gas reservoirs, then there is actually a lot you can do in other subject area. Why it doesn't go to the next slide? Let's see. Why is that? Yeah, it works now. Because, you know, this is, let's say, look at this formation, cross-section, and then yeah, you have all these various layers, and penetration of a liquid into that layer. If you can model this, actually, you are going to model flow of ink into paper, because this image is not from a geological formation. This is actually from a piece of paper. And the image shown on the left is penetration of a dyed ink into paper. So you see that there is a close link between geological porous media and industrial porous media. So that's what I would like to talk about that. I will give some more examples of this industrial porous media, talk about similarities and differences with geological media, and what is specific about industrial. And so the limitations of traditional modeling, we cannot really one-to-one use this exactly same models as in geological porous media for industrial, or even the experimental methods they will need some modification, refinement. So, and then the methods as well. So I talk about that also. One example of a industrial porous media is a liquid composite molding system. This is to make composites that is all around us. In the lower part of this slide, you see many examples of things that are made from composites. There are various ways to make composites. One of them is this resin molding, resin transfer molding. Very simply illustrated is as follows. You have certain mats. These are synthetic material. And you put them in a form to give them a given shape, desired shape, and that they close the form. There is an opening up here that you can inject a liquid resin, and that penetrates that layers of porous material. And once it fills, let it dry, it will cure and harden, becomes the solid material you want, the composite. Now, this is basically flow of liquid into a dry porous medium, just as happens when dry soil is invaded by water. It's a little more complex because of these layers you have there, and also because there would be heat generator. So you need to look at not only moisture transport, but heat transport. And this is actually in many other porous media. You have a complex, complex coupled processes. For example, fuel cells. I guess nowadays everyone knows about fuel cells. This is the image from a proton exchange membrane. These are made of 7 layers, and then there are also those channels around it. And these layers are all less than 1 millimeter thick, shown here at the lower right corner. 200 micron is this. This is the gas diffusion layer, and then connected to the macroporous layer. And you see that's fibrous material. The fibers are like 10 micron thick. So it's a complex layer system, porous system. As you know, air and hydrogen react, produce energy, but also they produce water, which is the waste. On the other hand, some parts of this fuel cell must remain moist, but you don't want too much water. So water management is a major issue. You need to know a lot about these porous materials and the modeling and so forth. In paper production, there's a very interesting examples of unsaturated flow in porous media. You know, they make paper from paper pulp. Paper pulp is basically water with a little bit of solid in there. It's less than 1% is the solid weight. And this must be turned around where we get paper that's more than 99% solid, and maybe there is some moisture of less than 1%, because you always have moisture in solids. And this is done in a paper factory, paper machine, and there are 5 main parts to a paper machine. There is where you make the pulp. Now, low consistency means it's very, very little solid. And then this pulp is taken to a forming section where as much as water possible is removed from it by gravity drainage and by vacuum. So that is done in the forming section. A large part of water, something like 75%, can be removed from here, but there's still a lot is left. And then at the end, the paper will be dried completely by drying, and that happens in the drying section. But drying requires a lot of energy. So you want to get water more than just gravity allows you, and that will happen in this pressing section. It is shown here that the share of forming and pressing and drying in removing water. The largest share is from just gravity drainage and pressing, but the energy that is required for drying is huge. That's why, so this is the energy that is needed for each process. That's why at this stage, you really should remove as much water as you can. This is done in the pressing section by moving the paper pulp that's shown here between two presses, two cylinders. And so the paper pulp that by now has about still 75% is water by weight. They put it on a felt. This is a piece of clothy material, which is extremely hydrophilic and very dry. And by pressing this paper pulp, the moisture is basically pushed and is sucked into this felt. And that reduces the amount of water to less than being 10% by weight, which then has to be removed the rest by drying. So this is another example of unsaturated flowing. There are many examples in ceramics, making of it, and in construction material, drying and wetting of food, in wood, in food industry, in plant tissues, drying of paint layers, in textile, making dresses, and also medical tablets, metal foam. Just goes on. I would like to give you two more interesting examples. These are things that we have worked on. One is that study of inkjet printing. How does ink penetrate into paper during inkjet printing? This is very important in the sense of optimizing the composition of the ink, the attachment to the paper, and reducing the amount of ink and so forth and so forth. So the ink, both paper and ink are complex materials. We have studied the paper. The coated paper has a coating layer and a base layer. Now here, in this example, the base layer is 85 micron thick, but it could be up to a couple of 100 micron, and the coating layer typically 15 micron to 20 micron thick. And there is, of course, coating on the other side as well. Now, this base layer is a fibrous material. It has pore sizes of 8 to 11 micron, and we can therefore use confocal laser microscopy to image that layer. And you can also use CT scanning to images. Here you see images from confocal laser that we have prepared ourselves. You can see the fibers very nicely, very clearly, their surfaces. And we can also see penetration of ink that has some fluorescent material in it into that paper. The coating layer, however, has very tiny pore sizes, 100 to 600 nanometer. And so we cannot use confocal laser microscopy. Instead, we need to use something like FIBSIM, focused ion beam, combined with the scanning electron microscopy. And then you can get a three-dimensional image of the structure of this confocal laser coating layer. And then we can put that into a digital image that can be used for porous scale modeling. A penetration of the movement of a liquid into that fibrous material is very complex. Here is a Nikon microscope that we have used for imaging, getting images like this. What you see, the green fibers of the fibrous layer, and then we are introducing some fluorescent dye from the right-hand side. What you see is that there are two fronts. One is that, see, the redder the color is, the higher the moisture is. And you can see that the fibers become red, and the space between fibers will actually become more saturated afterwards. So it's a sort of two-domain invasion of this ink into that fiber. And you can see that here very clearly. There are really two different fronts. We can also measure the thickness of the fibers. They swell as the liquid comes in, but then you see that on the right-hand side, this is time in second. This is the fiber, single fiber diameter, this particular fiber actually. You see that the thickness grows by 20–30%, and then it reduces again as the paper dries and the ink evaporates. And you can see the numbers here as well as a function of time. Now, here's another porous medium, interesting one. This is a diaper. It's a very complex material and with various functions and layers with various functions. This top sheet, the function is to carry away the liquid, the urine that comes as quickly as possible from the skin and not let it go back. So it goes into the acquisition layer, and the function of acquisition layer is that the urine comes at a point, it has to be distributed so that it will be delivered to the core where the main absorption happens. And the absorption happens by use of some material called superabsorbent polymer. It's an extremely hydrophilic polymer. It actually, water goes in there in huge amounts. You're talking about a gram of sap can absorb up to 1,000 grams of distilled water. And of course, if there are solutes in there, less will be absorbed. And in case of urine, 1 gram can absorb 30 grams of urine. So these are some glassy, stiff particles, a few hundred micron in the size. And then as the fluid enters, it becomes a gel-like, basically becomes water when it absorbs so much water, but still is a shape of a solid material. You see that absorption of water happening here. We started with particles under microscope, and this is real time. See, absorbed water becomes basically transparent. You can see that also here, a nice experiment we have, where we have a layer of particles in there, and then you see that happens fast. The absorbed by particles, they grow, fill up the glass, and because they are pushing against each other, they won't come out. So a similar experiment we did. Unfortunately, the colors are not very good. On the left-hand side, we have a thin layer of, we put a thin layer of particles in there, these sap particles. And then on the right-hand side, it is completely swollen and filled up that whole liquid. Then we, using camera, we looked at the rise of those surface of particles, and you see that here plotted as a function of time. And then we were able to simulate this process with discrete element method, and that is shown here. The particles are growing. Water is basically up to here, so it's growing into water. And what is interesting, you see that, let me stop it. Yeah, you see that red is higher pressure than blue. And what you see here is the pressure is, instead of being higher at the bottom, is lower at the bottom and is higher in the upper area because the sucking of water by these particles will create a suction and will move water down into that bed of particles. So this was all modeled and simulated, and we compared our simulations with the measurements that I showed you. So the dots are the height of these rising particles as measured, and then simulation is the line which is reasonably good. There are ways to improve that as well, actually. So what are the special features of this industrial porous media? One of the main features in most of them, not all, but most of, is that they are thin. The lateral dimension is much larger. They are often soft and highly deformable, have high porosity. Take a tissue, for example, has a porosity of 90% and is deformable. The paper is deformable. And so characterizing it is not straightforward. There are artifacts, experimental artifacts. We always have experimental artifacts when measurements of volumes or pressures, but these are in soil samples often negligible, but not in this media because you are dealing with small amounts. And so that makes determination of intrinsic permeability and capillary pressure saturation curves and so forth difficult with the standard setup. For example, we wanted to measure the in-plane permeability, intrinsic permeability of a sheet. Now, you cannot just use a standard permeability measurement setup. For through permeability, perpendicular is not much of a problem. You can use many layers and use that. But for through plane permeability, you cannot put more layers on top of each other because then there is the space between them. So we wanted to have one thin layer of a few hundred micron and have a setup to measure that. So we made a setup using a 3D printer where we basically created a very small indentation into a sheet of plastic. And then we could put, this is the top view, we could put our sample in there. And then we were injecting water, and also we did it with gas, and then measured the inflow pressure and outflow pressure. These are small pressure differences. And then we had measured the amount of water that is or liquid fluid that would go through, and therefore we're able to measure permeability. But as I said, we deal with small volumes and small pressure differences, so you really need very accurate measurements. This is for measuring a standard way of measuring, one of the standard ways of measuring capillary pressure saturation curves for a sheet. So the sheet is put here, is this one here. Okay. And this is a standard pressure cell apparatus. It's also used for soils. And so there is a membrane here that is very hydrophilic and doesn't let the gas to go through. And so here we have a reservoir of water that always remains full with water. There is no gas going in there. And a balance measures the change of weight of water in here. And that corresponds to the weight of water change in the membrane, in the sample. We put a weight there to, this is about 14 PSI. This is to mimic a baby sitting on the sheet. And then you can do drainage and measurement. So for example, if you want to do drainage, you start with putting a dry sheet there and then let it fill up with water and then increase the gas pressure in order to eject that water from the sample. You can also do imbibition, of course, where you have very high gas pressure, where you put the sheet of dry sheet there, and then decrease the gas pressure slowly in order to let the water come in. And you can do that in steps and measure the capillary pressure saturation curves. Now, one of the things is that when the water enters this sample, it will also accumulate around the sample in this corner, all around it. It's a round sample. or it will also, oh, what's that? Oh, I'm sorry. Okay, it will also accumulate here. And in those corners, now these are tiny amounts, but volume of the pores of the sample are not large either. So you really have to have ways in order to minimize this volume as much as possible, or you should be able to determine those volumes as well. So that's, and we have done that and this was also published by making a certain, the side of the sample hydrophobic, making the side of the container hydrophobic, and that sort of effects. Now, these are typical PCS curve for a certain paper sample that we had. Something is covering. Yeah, I hope this is going up. Yeah, and this appearing. Yeah. And then you can do this experiment with, by the way, sorry, this was not paper, this was a layer of diaper. And you can do it with 1 layer or with 3 layers or 10 layers. So here is, we compare 1 layer and 10 layer, and we see that when we had not really modified our setup, we got different results than, this is the red, than when we did the modified results. Then 1 layer and 10 layer gave us the same curves. You can see that here, but the red is slightly different. One thing interesting about this data is that each curve for drainage and imbibition takes 12 hours. So you get a curve that gives you a relationship between PC and saturation, but that relationship is developed over 12 hours. It has to be done very slowly. Whereas the process in a diaper, as you know, happens in 10 seconds or 30 seconds, going from dry to wet. So process is much faster. And the question is, okay, if the process of wetting is much faster, will you really, can you use these curves, or do you have to do something else? And so we did that experiment in the same setup. As I said, we can start with a dry sample and with a very high air pressure, and then reduce the air pressure. Now, if you do it in small increments, you get the typical capillary pressure saturation curves. But in one experiment, we decreased the air pressure drastically so that the layer could get wet in very short time, as happens. And then the data are like this, the green. As you can see, it in very short time, it goes to some large value and then almost a flat plateau. So now you should be able to simulate this. And you can simulate it with Richard's model, having only saturated. But you can also say, yeah, but the air is under pressure, therefore it takes time. We know how long it takes for reducing the air pressure, because it doesn't happen in 0 time, to some very low value. It takes some time, so we include that, and so we do a 2-phase flow model. Both of them really give you the same data, the same curve, and it's different from the measured data. This was one type of tissue, and then we did it with 2 other type of tissues. They were a little thinner. And so again, the symbols are the measurements and the curves are the simulations. We don't get a real nice fit. So here we believe the dynamic capillarity effect is important, because in those theories, Richard's model, standard 2-phase flow, it's assumed that water, non-wetting phase pressure and wetting phase pressure are in equilibrium with the saturation that is there. Whereas in this experiment, now the air pressure is really very closely fast is decreased, whereas the water pressure doesn't change as fast as much to be able to follow this relationship. So instead, as some of you may know, we have a dynamic effect that will say that these two pressures are not equal to the capillary pressure corresponding at the given saturation, but you have to have this extra term, and tau is a coefficient that accounts for the delay in the equilibration of pressure of the two phases. It can be measured, and here we fitted tau values, and you see that we got very good fits. The tau value here are small because these are very thin layers, a few thousand pascals second. So see, this is one of the things that differs with a lot of geological porous media. Processes often happen fast. In the pressing of paper pulp I mentioned to you, it moves through the paper pulp, and the felt move between press as tens of meters per second fast. And so the imbibition really happens really fast. Whereas for that felt, if you measure PCS curve, you need a day to get the PCS curve for that felt. So processes happen fast, therefore dynamic effect is often important. Now, another aspect is that, as I said, the lateral dimensions are much bigger. You have a thin porous medium. So for example, here you see that the size of this layer is 150 micron. And then the fibers are 20 micron, 10 to 20 micron. They are not much smaller than the thickness. So the question is, can you really treat this as a continuum and use models of macro scale models to model flow through this by discretizing this layer? The answer is, in my view, well, it's not really admissible based on principles of macroscopization. You know that when you use macro scale models, that means you use average quantities, average over a representative elementary volume, an REV. Now, there are requirements for this REV, that its size must be much larger than the pore sizes or grain sizes, and much smaller than the domain size. Now, for this what I showed you was from a paper. Now, we did the measurement of porosity for different REV sizes. We took the whole thickness of the paper, and you see that even when you take the whole thickness of the paper, in the lateral direction, you need 200 micron, or actually 400 micron, before it reaches a plateau. So this means that macro scale theories are not valid in this range of macroscopic REV sizes. And in the paper that I just showed you, the REV size is equal to the thickness of the paper. So you really cannot say I have many REVs over the thickness of paper. We cannot fulfill the restriction that is here.
Okay.
All right. So here I also show you that basically the main message is that the REV size is comparable to the domain size as not much larger than the pore sizes. And here you see permeability as a function of the domain lateral size. Again, you need an REVC size that is comparable. And by the way, on the right-hand side, we see von Genuchten parameters. And we see that we need the same sort of REV. So if the REV size cannot be defined, can we use macroscale theories? Another issue is that often we have a stack of thin porous material that stack on top of each other. Now, a thin porous media is one piece of porous material, but the space between two layers, yeah, it's not really a porous medium, it's a space. How do you model that? If you do 3D modeling, you can discretize the layer, and then apply Darcy's law there, but what do you do with the space between it? How do you do that? How do you discretize that or model it? And that space is really important, is really affecting the process. And to show that here, this is a piece of paper which is 250 micron thick. And we have put a stain on that paper. That's the pink stain. And then we took two papers of each 120 micron thick. So the total thickness is exactly the same as the previous one. And then we put a stain on the top layer. Now, in the left-hand side, the domain that was stained is exactly the same on both and bottom and top. So if you turn around the paper, you see the same stain. But on the right-hand side, you see that the lower layer hasn't received as much liquid as the upper layer. This is because there is a space between them. So that really affects it. And you can see that here, these are again two thin sheets from diaper that are put together. And if you press it, yeah, it looks like that the space has disappeared, but actually you see that here, the left-hand side is uncompressed, the right-hand side are compressed. And then you can see that there is still a space between them, and the liquid distribution in the left side, here is the liquid, the red, see there is pink, there are fibers, and the red is the liquid. There is liquid on the top layer, nothing in the lower layer. On the right-hand side, you see a lot more red on the upper layer than the lower layer. So it doesn't really distribute evenly between the two layers. In one layer, it distributes nicely, but not to the next layer. So whether it's two pieces of 120 or one piece of 240 makes a huge difference. So we have, the question is, how do you model that? And one way to model such layer where the REV cannot be defined for it is to do pore scale modeling. The advantage of these industrial porous media often is that they are sizes you can hold in your hand. You can put under microscope. It's not like geological formations that you can only put a borehole in there or take a sample out and study and make conclusions about the whole reservoir. Here, you have everything in your hands and you can image the whole thing. So you have the whole pore space, and therefore, why not do pore scale modeling? Of course, there are various ways, but often they are also very computationally expensive. Therefore, it would be still nice to have a macro scale approach, especially if you have a large sheet, for example, as in a diaper, in a paper, you have a large sheet, or also in fuel cells, although the size is not big, but if you want to simulate a fuel cell stack, then you cannot really do pore scale modeling. So that would be nice to have a macro scale modeling. And for that, we are, instead of the traditional three-dimensional porous media, which requires to be able to define REV over the thickness as well, we use what we call reduced continuum model. And in the reduced continuum model, we basically do REV averaging, but then the REV size is equal to the size of the layer. So we don't have REV moving over the thickness. There's one REV over the thickness, and then of course, many REVs laterally, which means that when you do the averaging, you don't get three-dimensional equations, you only get two-dimensional equations. But you get one set of equations for layer 1, two-dimensional, one set of equations for layer 2, one set of equations for layer 3, and then they exchange with each other mass, momentum, energy, and entropy, and so on. So this means that we derive equations of conservation first, then we use the rational thermodynamics in order to obtain constitutive equations. I'm not going to go through that, but the three layers that are very thick layers with some thickness, they are modeled at the macro scale as zero thickness domains. So they are zero thickness and they are only have an order with respect to each other. One is on top, one is in the middle, one is bottom, and exchange with each other thermodynamic quantities. So this means that we have one equation for, and that's the equation here, one equation for the top layer. In this case, this is continuity equation. Change of saturation as a function of time is as a result of lateral fluxes. So the fluxes are lateral, but then there is exchange of mass between upper layer and lower layer. That's this one. As you can see, it's negative here. And then there is from top, something comes into the upper layer, and at bottom, something leaves the lower layer. So those are the governing equations. As you see, there is no gradient in the z direction anymore, only in the x and y direction. This is very nice because the properties then you need are all average properties that are average over the thickness of the layer. We don't need to give properties as a function of thickness, for example, the depth of the z direction. So there was an experiment that we did. I'm going to finish in 5 minutes. This was done at Procter & Gamble research site in near Frankfurt, where we put two layers. You see those are the two gray layers on top of each other, but the upper layer is completely wet. And then we put them on top of this instrument called NMR mouse, nuclear magnetic resonance measurement, that can measure the average saturation of each layer. So and it measures it really over the whole layer. So we don't have, we don't get distribution as a function of X, Y, or Z. So for each layer, we just get one average saturation. Now, the layers being homogeneous reasonably, then we say, okay, that's fine. We can use that as our data. So we get that here. The blue is the top layer. You see that it's a saturation. By the way, I didn't say it completely correctly. The top layer is not completely moist when we put it there. No, we rain water on top layer. Okay, so as you see, the saturation of the top layer increases as we rain water on top of it, and it reaches a plateau at some point, and then we stop raining, and the lower layer starts receiving water after some time. It takes time for it to receive water. It doesn't react immediately. It eventually reaches the same saturation as the upper layer, but it takes time, it's delayed. So can we model this with Richard's equation, for example? And that has been done, and the result is the green line for the top layer and the brown for the lower layer, the dashed line. As you can see, they are far from the measured values. I must tell you that we were able to get the porosity as a function of depth because we did the imaging, and we defined 14 sublayers for each layer for our modeling, Richard's equation. We really put the real value of porosity. We also constructed PCS curve for those sublayers. So we broke it into 14 sublayers. We did really, that was our also a numerical grid, and we didn't get any fit. And whereas when we use our equations, you can get a very nice fit. I must say we fitted the value of this exchange coefficient. By the way, this exchange coefficient, it is a property of the space between the two layers, because it tells you that the pressure difference between the two layers is the driving for exchange of water, and then there is a transfer coefficient, a mass transfer coefficient, and that's a property of the thickness, the space between them. If you push the two layers together, that coefficient will increase. And if they are not pushed against each other, the space is bigger, the coefficient will become smaller. So I think I'm going to end here. I'm sorry about the issues with the presentation. I let you read the conclusion, and as the time is past, and I hope we have time for questions.